as long as it's smaller than that.
Okay.
I figured you would get to it. Yeah, I know.
Yeah, unfortunately, we're gonna have to wait till tomorrow. I'll do it tomorrow.
Wait, then you can't get into 50 because there's like.
Yeah, then you have to get into like 36.
There's some hydrogen stuff in there, acid stuff in there.
So, yeah. Well, yeah, skip those. Yeah.
Yeah.
For now. We'll come back.
So we don't have to do
Well, I'll have enough for you to do tonight. All right, moving on. Now, we did this on Friday. We talked on Friday about comparing the solubility of two things. If they give out the same number of ions, you just compare the Ks. If they don't give off the same number of ions, like this gives off 2 ions, this breaks down into 3 ions. So what you have to do is not just compare the Ks, but take the correct root of these K values and then compare them, if you want to know which one is more soluble. Just because this is a bigger K value does not make this more soluble. It turns out it's not more soluble. This one is more soluble because this breaks up into 2 ions, so we have to take the square root of this to find our solubility, or X term. For this one, we have to take the cube root of it. This breaks up into 3 ions, 1 of those and 2 of those. So we have 3 X terms that are given off there. Taking the cube root of that is going to give us 10 to the negative 5th. That's bigger than 10 to the negative 6th or so from that one. So yeah, I'm hoping that you caught that on Friday, and I wasn't planning to spend any more time on that. Common ion effect, that was what was on our reading quiz. I don't think that we need to go through a whole lot of instruction on that. I think that we could do it. Let's take a look at the problem. Calculate the solubility of calcium phosphate in a 0.2 molar solution of sodium phosphate.
Oh, I got like the last chapter over again.
So we have a beaker that has sodium phosphate in it. Now we're going to dump in some calcium phosphate. So the calcium phosphate is going to try to dissolve and give off some of each of those. But this dissolving process has a common ion. There's already some phosphate ion there. So that has to be included initially.
So negative 32.
Yeah, negative 32.
That's ridiculous.
So we want to calculate the solubility. We're finding this thing right here. Would you go ahead and try to do that? That's going to go down by x. It is going to shift to the right because that term is 0, so it's going to go down by x. Solve for x, and that's going to be the answer. Yes, sir.
How can you neglect any if we're counting C? Like, why is that the only ion that's included?
Why is that what?
The only ion that's not included. And
It's not included.
Doesn't react.
like it, we just like leave it out.
Which one is being left out?
Sodium.
And then
Oh, the Na presence has nothing to do with this thing dissolving. So we don't care about the sodium. But the phosphate from this does have something very much to do with this dissolving process because this thing is trying to dissolve, but there's already some of that that's present in the solution. So that's going to affect how much that dissolves. The sodium, there can be a small amount or a lot of sodium. It doesn't matter because sodium doesn't interact with anything else in water. But the phosphate definitely does interact. And so remember, the equilibrium is where a reaction gets to its most comfortable position of ratio of products to reactants. Since sodium is not a product nor a reactant, we don't care about it. But the phosphate we do, it's one of our products.
but don't we have to do a quadratic formula for this one?
No,
No? Is
you'd
the
have to
x
use some
negligible?
formula that gets the root of a 5th order polynomial.
Fifth?
Oh.
Wait.
Wait,
Oh,
what?
Wait.
I forgot.
Oh wow.
Wow.
Just try it. Fill the ice table out and see what you have to do. You're trying to get that X term.
wait, don't reveal it.
I'm not saying anything, I'm just writing some things. Don't look.
No, you're not supposed to do that.
Don't look!
So I mean,
Submit a
like,
bunch of
I got
times.
it completely different thing.
I grabbed it. That's not quadratic. It's like it's pointed.
He gives it my cup.
It's 3 to
So
30.
confusing.
That's all. It's 0.2.
You were not supposed to look.
You never made it.
Yes?
For the point 20 molarity, can we just say 2 times with point 20? Because just, you know, it's like, well, I just like for the change, I just like multiplied by 2 because it has a 2 But I think I'm forgetting like the first chapter that we did.
You made that a 0.4?
Yeah.
No!
No.
Wait, but
Because you have a beaker that's 0.2 molar sodium phosphate, right? So that means the concentration of sodium is 0.6, and the concentration of phosphate is 0.2 because there's one phosphate in every one molecule. So the phosphate is in there. Its concentration is 0.2 molarity. Just because there's a 2 there in the dissolving of this does not suddenly double the concentration of phosphate. Now the 2x, that's the part that you need to double because the amount that this goes down, every one of these gives off 2 phosphates, so I counted for it here.
Mr. Moore,
Yes?
if you square that 0.20 plus 2x, wouldn't that give you a quadratic though?
Yeah, but then it's being multiplied by a cubic.
9x cubed.
Oh, yeah.
What is that? Okay. Well,
What x cubed?
No, I do.
9x.
What?
Oh, I'm a 27.
There we go.
Oh, yeah.
Yes.
You can't.
Why wouldn't it be like
No, I don't know if that's right.
instead of 3x and then 1x? Like for the, remember
What is
the
this?
question about AG plus and how it's 2AG plus, but we didn't multiply by 2?
This one or the next one? Back.
I'm confused.
This one?
Me too.
We did multiply by
I
2.
don't see how you can just take the
No, the one.
fifth root.
Oh, wait.
Yeah, that one.
Wait
Oh,
a minute.
because the question said this. The concentration of silver is 2.2 times 10 to the negative 4. They're
You do?
telling us
I get
what
it.
this
How?
concentration was.
But since it's 2,
How do you just take the fifth root then?
No.
So I'm-
When you start with this and you know how much of this goes down, double that to get to this. But the question is telling you they know how much of this was present at equilibrium. That means half of that is how much of that dissolved. We're still using the 2-to-1 ratio, but this was given to us. You don't take what's given to you and double it because there's a 2 in front of it. You take it, okay, that concentration is 2.2 times 10 to the negative 4.
oh,
So that was given to us. If this is given to us, then yeah, we take that and multiply by 2 to get that. But it wasn't. That's what was our given information. Yes, ma'am.
Can you go back to
The one
the.
before.
Yeah. Okay, so. No. The
next
one
one.
with the 27x.
Oh yeah.
Okay. For this one, would you set 27x cubed equals to that and then the other things there?
No. Here's what we have to multiply all this out to solve for x. However, what are we going to do about this math?
It's ugly.
What can you say about the size of x? Here's our k value, 10 to the negative 32 power. Does it shift far to the right?
Yes. No, I mean, like relief. No.
Does it shift far to
It
the right?
doesn't.
No. That means that plus 2x is going to be a very small number, especially compared to 0.2. Neglected.
Hey. Okay, yeah.
Okay, that makes our work much nicer. Now we don't have a 5th order polynomial or a 5th power polynomial. We have a 3rd x cubed.
Your notes are messy.
I don't care.
Well,
I can.
I guess
If I can think with this, that's
What do you
fine.
want to neglect?
You can neglect the 3x too.
Yeah, do
Why?
No,
neglect
because it's
everything?
much different from
Compared
0.
to.
Even if it's tiny, it's infinitely different from 0. But when this is tiny, then that's not much different from 0.20, right? It doesn't change the 0.20 there. So anytime you have 0, you cannot neglect the change in x. Anytime you don't have a 0 there, if the x is tiny compared to it, then you just neglect the added part.
And we compare the 5% rule with the starting concentration rate.
Yes. Artea?
So,
But if it bothers you, then just multiply all this out, keep the plus 2x, and tell your calculator to solve that polynomial.
Yeah, but maybe-
And you'll have what? How many roots?
5.
5 roots, possibly. It's going to be a,
Quintic.
gosh,
Just graph it.
from down, it's going to go down, up, and then down, up, down, up. Yeah.
But you'll
So you
get
have
5
5x.
x's.
Well, since it's a cubic, it's just one use though.
That's going to be a fifth power if you keep that plus
in.
2x.
But it won't go up and down as many times.
Why?
Because that's a perfect cube. Which means that there's only one root.
Oh, because it's a I see. Anyway, I'm neglecting that plus 2x term, solving for the x, and getting an x value of, I can't remember this one. 10 to the negative what?
no, I got 2.3 to the negative 11, but I don't know if that's still not right.
Just do that.
Yes, I think that's right. 2.3 times 10 to the negative 11.
I don't think that's so small.
Does anybody else have that? 'Cause
Compared
you
to
get-
32, it's much bigger.
No, and listen, everybody look up here. The reason this concentration is so small, the reason that this calcium phosphate does not dissolve very much was because of the presence of that at the beginning. It would have dissolved a lot more if that was not there. But since that was present, it does not allow the shift to go as far to the right. That's what the common ion effect means. It means that if you already have one of your products, even though there was 0 of that at the beginning, that presence keeps it from going too far to the right because you're going to hit equilibrium sooner. Yes, ma'am.
If you did the graphing thing, how would you know which one's the right root?
Wow, Rob, you're going to.
Well, I don't
Well,
like
it would, let's see. Yeah, I think you'd have to plug it back into here and see what would be a reasonable.
So that's just making more work for yourself.
Yeah. Yeah, I think you're only one of these. Don't do the graphing method on this 5% rule. Let's cancel it out.
Does it always
Yes,
work?
Artea?
So, you're saying that the constant has such a low pace speed.
Guys, can't hear the question. Sorry. Go ahead.
Your conclusion is because it has such a low pace speed that it doesn't really shift.
It does not go far that way. So that plus 2x is going to be a very small number because x is so small.
Because 0.20 is like a lot more than the. Like,
Yes.
the
Yeah, look at that x value. 10 to the negative 11th power. Add 10 to the negative 11th plus 0.2. That's 10 to the negative 11th. Even though it's being multiplied by 2, that's minuscule.
So we just like compare the pace speed with like the molarity. It's like it's not really like the molarity is like really big.
Right,
Like,
that's
and
right.
the
That's
pace
what the
is
5% rule is about. Yep.
Thanks.
All right, gang, we move on.
I don't like.
Well, this is what our reading assignment is tomorrow. I'm not going to leave that up for too long because you got to
Oh.
read a page.
Come on.
Okay, now the last thing for today, how are we doing?
Great.
About 15 minutes left. The last thing for today is you need to be able to determine if you have certain concentrations of ions, will they be high enough to form a precipitate? I want to show you 2 examples. That's what I'm hoping for. So I want to suggest that you copy this down, and then let's go over a couple of examples. One, I'm going to just
Huh?
take out of the book.
Water. Rain. Actually. It just disappeared. Artie, the cues are back.
The dilute concentrations, that might not make any sense yet, but when you see a problem, you say, oh.